Hello everyone, welcome to course study on solid mechanics. In today's lecture, we are going to discuss the concept of stresses, strain and deformation in the determinate shafts of composite cross-section. Remember that in previous lectures, we have discussed the concept of homogeneous cross-section, and in today's lecture, we will discuss the concept of composite cross-section. So, we will move for the composite cross-section. So, what does it mean? Composite cross-section is nothing but shafts are connected in parallel. The two shafts of different material are connected parallel to each other and it will work as a one unit. So the definition will be as follows. When one shaft is connected to the other shaft so as to surround it, then it is said to be connected in parallel. Okay, two shafts of different material are connected in parallel. Okay, in parallel shaft, two shaft will behave like a single shaft or as a single unit. Okay, so from this figure you can see that the shaft 1 gets surrounded by the shaft 2. Shaft 1 is surrounded by the shaft 2 and it is subjected to torque T at both the end. Okay, so for such a system, for the shafts in parallel, we have two equations to be considered. The first equation is total torque transmitted will be shared by two shafts. So this total torque will be shared by both the shaft, that is 1 and 2. Okay, therefore T will be equal to T1 plus T2. This is the first equation we have to consider for the shafts in parallel. The second equation which we have to consider is the angle of twist remains same for both the shaft, that is theta 1 equal to theta 2. Is it okay? So based on these two conditions, we are going to solve a numerical for the shafts in parallel. So the numerical statement is as follows. A composite shaft consists of copper rod of 30 mm diameter enclosed in a steel tube of external diameter 40 mm and 5 mm thick. The shaft is required to transmit a torque of 0.5 kN. Determine the shearing stresses developed in a copper and steel. If both the shafts have equal length and welded to a plate at its end so that their twists are equal, take G of copper equal to 40 GPa and G of steel equal to 80 GPa. So the given data as per the statement is the diameter of the copper is 30 mm, the external diameter of the steel tube is 40 mm, as the thickness is 5 mm, therefore the internal diameter of the steel tube will be the 30 mm, because 40 minus 10 will be the 30 mm because thickness is 5 mm, and the value of torque is also given, that is 0.5 kilonewton meter. Remember that this torque will be the total torque, and this total torque can be shared by torque of copper plus torque of steel. Okay, so we will discuss this concept in the next slide. The value of G for copper is 40 GPa and steel it is 80 GPa. So first of all we will calculate the value of J for the copper, J for the steel. Okay, the polar moment of inertia for the copper is given by pi by 32 into d raised to 4, but the diameter is 30 mm, so it will become pi by 32 into 30 raised to 4 and the value will be 79.52 into 10 raised to 3 mm raised to 4. This is the value of polar moment of inertia for the copper shaft. For the steel shaft, the polar moment of inertia can be given by pi by 32 into capital D raised to 4 minus small d raised to 4. Now, if you read the statement carefully, you will observe that steel shaft will be work as a hollow shaft because it has an external diameter, again it has a thickness also, so external thickness it will work as a hollow shaft. So for the hollow shaft of the steel we have polar moment of inertia 171.805 into 10 raised to 3 mm raised to 4. So in this manner we have find out the value of J for copper and J for steel. So as discussed in the previous slide, we have total torque shared by T1 plus T2. So in our case, this total torque will be shared by copper plus steel. The value of total torque as given is 0.5 kilonewton meter. We have to convert it into Newton mm. Therefore, in Newton mm, it will become 0.5 into 10 raised to 6, which is equal to Tc plus Ts. And we can see it as a equation number 1. Okay, the second governing equation is the angle of twist in both the shaft will be same. That is, theta of copper will be equal to theta of steel. And the theta can be given by TL upon GJ. Okay, for both the shaft. Okay, so as per the statement, we have length same in both the shaft, in steel also and in copper also. So the length will get cancelled. So the remaining equation will be TC upon GC JC, that is T upon GJ of copper equal to T upon GJ of steel. So on putting all those values which are given in the numerical and which we have calculated for the polar moment of inertia, we have one equation, that is TC is equal to 0.231 TS, that is torque in copper is equal to 0.231 of torque of steel. This is the equation number 2. If I put the equation 2 in equation 1, we will have the value of torque in steel, that is 406.033 into 10 raised to 3 Newton mm. This is the value of torque in steel. Okay, once you know the value of torque in steel, from equation 2 you will have torque in copper, that is 93.79 into 10 raised to 3 Newton mm. So by using these two conditions, that is total torque shared by the both the shaft and theta will be same in both the shaft, we have find out the value of torque in both the shaft. Once you know the value of torque in both the shaft, you can easily find out the value of shear stresses. And as per the torsional formula, we will consider into these two equations, tau of copper upon R of copper, which is equal to T of copper upon J of copper. Okay, so from this equation we have shear stress into the copper is equal to RC upon JC into TC. So on putting all those values which we have calculated, we have stresses in steel 17.69 MPa. Okay, and in the same manner we have stresses, actually stresses in copper it is 17.69 MPa, and the stresses in steel will be 47.266 MPa. Okay, this is the value of shear stress in copper and this is the value of shear stress in steel. So in this manner, by considering the two governing equation, we have find out the value of shear stresses in both the shaft. Okay, so in the next lecture we will discuss the last concept of it, stresses, strain and the deformation in indeterminate shaft. We will stop here. Thank you.